Volume 181, Harper's Magazine, June 1940. Enter Atomic Power. By John J. O'Neill. Science has won the first great objective in its quarter-of-a-century struggle to release the vast store of energy locked up in the hearts of atoms and to make atomic power available to man. In revealing this secret, it has presented to the human race a great problem and a great opportunity. Out of the laboratory has come the announcement that there has been isolated a new strange substance of fantastic properties, which can release tremendously vast quantities of atomic energy by a very simple self-sustaining process. This new substance has heretofore remained hidden in the same material from which radium is obtained. It is many millions of times more plentiful than radium and gives out billions of times more energy. Radium sputters like a damp fuse, but the atoms of the new substance explode catastrophically when disturbed in the right way, and each one that explodes sets off two others, thus providing the chain reaction that makes available a practical means for obtaining a steady controlled flow of atomic energy at a rate 5 million times greater than that obtained by the burning of coal. It is the first step toward releasing the total energy content of atoms which, weight for weight, is 18 billion greater than that yielded by any chemical combustion process. Science has cleared the way on theoretical and experimental grounds, and the course now lies open for the engineers to enter and make the practical application of atomic power, which may open a new era for civilization. All that remains to be done in order to unleash the vast quantities of energy bound up in matter is to work out a practical method for separating the new substance from the material in which it is found. This has been accomplished on a laboratory scale, and several processes for a larger scale production are now being worked out. The way around all obstacles now seems clear, although before they have been passed, the engineers will undoubtedly gather some new observations about the innate perversity of inanimate matter. The new substance which made possible man's first successful attempt to release atomic energy is called uranium-235, the number indicating its atomic weight. It is a chemical twin to ordinary uranium, the heaviest naturally occurring chemical element, which has an atomic weight of 238. Isolation of this substance in experimental quantities was achieved by Professor A. O'Neill, 30-year-old physicist of the University of Minnesota. He isolated only a few trillionths of a pound, but that was enough of the substance to permit the making of exceedingly important and significant experiments in a scientific laboratory at Columbia University. Experiments that open up possibilities to stagger the imagination. Professor Neill isolated not only uranium-235, but he separated all three components of uranium, the third being uranium-234. Uranium-235 occurs in nature in uranium-238 to the extent of 0.75%, uranium-234 being present to a little less than 1/10 of this amount. All three of these isotopes have almost identical chemical properties and differ mainly in their masses. Professor Neill used this difference to effect the separation. He passed the electrified vapor of uranium bromide through a combination electric and magnetic field, which caused the three different kinds of atoms to traverse different paths and be deposited on different spots on a platinum plate. The separation of these isotopes was not performed by Professor Neill as a happenstance experiment. The whole scientific world interested in nuclear physics had been on its knees for a year, pleading with every scientist who was in a position to attempt to separate these isotopes to make the effort. Since it was obvious from earlier experiments that even small samples of pure uranium-235 and uranium-238 would make it possible in a single series of tests to get a clear-cut answer to the question of whether man would be able to solve right now the scientific problem of the release of atomic energy on a practical scale. He was one of the few men in the world competent to handle the difficult task. And he succeeded. In January 1939, an experiment was made on uranium atoms with startling results. Professor John R. Dunning of Columbia University and Dr. Enrico Fermi, Nobel Prize winner of Italy, who had recently joined the Columbia staff, succeeded in splitting the uranium atom and observed a tremendous release of energy. 200 million electron volts from each atom disintegrated. This was a sufficient amount of energy to make the process a continuous one. since there was not only a great excess of energy produced, but in addition, enough secondary projectiles were released from each exploded atom to shatter at least 2 additional atoms. In later experiments, when large amounts of material were bombarded, the material should have, on theoretical grounds, completely exploded in the briefest fraction of a second with cataclysmic results. The material got hot, but it did not explode. The reason the uranium did not explode was a mystery. While Professor Dunning and Dr. Fermi were the first ones in this country to perform the uranium splitting experiment, it had previously been performed in Europe. But there was a delay in publishing the results and, as a consequence, experiments giving similar results were performed in 3 laboratories in as many countries within a space of about 2 weeks. Doctors O. Hahn and E. Strassmann in the Kaiser Wilhelm Institute in Berlin, and Drs. Frisch and Meitner in Copenhagen anticipated the Columbia results, and L. R. Hofstad, R. B. Roberts, and M. A. Tuva of the Department of Terrestrial Magnetism of the Carnegie Institution of Washington followed a few days later. It was as if several armies, all approaching an objective from different directions, arrived at the predetermined goal at about the same time. 2. Splitting of the uranium atom was achieved with surprising ease. This is the heaviest of all atoms. From experience gained in smashing lighter atoms, it was expected that it would be necessary to hit the uranium atom with a tremendously powerful projectile in order to crash through the 92 units of negative electrical fortification in the outer electron shell, and its 92 units of positive electrical fortification concentrated in the nucleus. Powerful electrical bombardment machines had been designed for this purpose. The most successful was the cyclotron, developed by Professor O. E. Lawrence, Nobel Prize winner, of the University of California, which uses relatively low voltages but whirls electrified particles in a combination electric and magnetic field until they attain very high velocities and issue from the machine in a beam with energies equivalent to 25 million volts. A new large cyclotron, the world's largest, is now being constructed by Professor Lawrence. It will produce a disintegrating beam of several 100 million volts, and it is expected to be powerful enough to smash practically all atoms. But these powerful projectiles proved to be unnecessary for the direct smashing of the uranium-235 atom, although the cyclotron was used in securing the initial supply of neutrons necessary to start the process, analogous to a match in starting a fire. Instead of a powerful blow being required to smash the uranium-235 atom, it was shattered by a relatively gentle blow. A tuning technique proved to be far more effective than brute strength. When the neutron, an unelectrified particle and one of the fundamental building blocks of matter, travels at high velocities, it shoots past atoms and acts as if it did not know they were there. The atoms reciprocate. But when the neutron is slowed down to a very low velocity, equivalent to about 1/30th of an electron volt, it and the nearby atoms become tuned to one another. The neutron then enters the nucleus of the atom with as much ease as if it were falling into a hole. The neutron and most atoms act as if they were enlarged with respect to one another. When neutrons travel at slow speed, one element shows an enlargement of about 4,000 diameters. Paradoxically, the slower neutrons are, the more effective they become. This peculiar phenomenon is likely to play an important part in practical atomic power control processes. When the ordinary uranium atoms were bombarded last year, and only a certain number of the atoms responded with explosions and others appeared immune to bombardment, thus preventing the general release of atomic energy, it became apparent that the uranium being treated was not uniform throughout, but contained some responsive and some non-responsive factors. It was known for a long time that uranium contained 3 isotopes, or chemical twins, 234, 235, and 238, and it was suspected that the 235 was the responsive factor and that the 238 prevented it from giving its full possible response. In order to test this theory, it would be necessary to obtain samples of each of the isotopes entirely free from contamination by the others, so that each could be bombarded separately and its individual response determined. This would be the critical test which would determine if the atomic power dream could be translated into reality. But the isolated isotopes did not exist anywhere in the world at that time. When Professor Neill made them available in extremely tiny quantities, the experiment was quickly made and it gave a clear-cut and spectacular answer. It was the open sesame to nature's treasure chest of atomic energy. The two principal isotopes were tested separately. Professor Dunning and his associates at Columbia placed the small platinum plate containing the uranium-238 deposit in the cyclotron and went to the control board in an adjoining room where are located the control apparatus for operating the cyclotron and the recording instruments that tell what is taking place in the bombardment chamber. The cyclotron is almost entirely surrounded by tanks of water from floor to ceiling to protect the workers from the burst of neutron gas that comes from the bombardment chamber and goes through ordinary matter like water through a sieve, but is shut off easily by water. This is what makes remote control necessary. When the cyclotron was started with the uranium-238 in the bombardment chamber, the recording instruments indicated a few spasmodic bursts of energy release per minute. The heavy uranium was taken out of the bombardment chamber, and the cyclotron operated with the chamber empty. The recording instruments continued to indicate a few energy bursts per minute. The difference between the results when the chamber contained the heavy uranium and when it was empty was very slight. When the light uranium, the 235 isotope, was placed in the bombardment chamber, the situation changed completely. The instruments recorded intense activity. The counters attached to them that click for every 10 bursts kept up a barrage of sound like a machine gun. The wavy line on the oscilloscope that recorded each energy burst stayed almost constantly at the 200 million electron volt level. The uranium-235 atoms were being smashed at a rate 10,000 times and more faster than the uranium-238 atoms. Repetitions of the experiments under a variety of conditions gave the same results. A series of auxiliary experiments checking up the results of the main experiments were made, and each gave additional evidence of the correctness of the conclusions indicated. The experiment that marked the climax of 25 years of effort by scientists all over the world to smash their way into the nucleus of the atom and release the tremendous stores of energy located there had been performed. There are many gates to the reservoir of atomic energy, and one of them had been opened. The story which this experiment told, in non-scientific language, is this. A new substance, uranium-235, which releases atomic energy easily, has been isolated. 1 gram of its mass contains a total energy of about 11,700,000 kilowatt-hours of electricity, of which about 1/10% can be annihilated and released as the equivalent of 11,700 kilowatt-hours of electricity, or about 5 million times more energy than can be obtained from burning an equal weight of coal. Until, however, certain very real technical problems are solved, atomic power must remain a scientific laboratory accomplishment. It must be kept in mind, too, that the experiments with microscopically small amounts of material must be repeated many times with successively larger quantities as they become available. 3. The knowledge gained from these recent Columbia experiments and previous experiments in universities in various parts of the world enabled scientists to understand why ordinary uranium in last year's experiments did not yield a continuous flow or an explosive release of atomic energy, and also to gain an insight into the processes by which the practical utilization of atomic energy will be affected. They knew that ordinary uranium contains 139 atoms of the isotope 238 for every atom of the isotope 235, and 17,000 for every one of the 234 isotope. The mixture was bombarded with neutrons slowed down by water. Some of the bombarding neutrons reached atoms of the 235 isotope and smashed them. Each of the smashed atoms gave off 2 or more neutrons, which were slowed down by the surrounding water, and returned to the uranium to smash more atoms in addition to those which would be smashed by the neutrons in the primary bombardment from the cyclotron. Instead of there being a resulting increase in the number of atoms smashed, the process appeared to slow down slightly. The new experiments at Columbia tell the story of what was happening and point the way to success. The slowing down was due to the fact that the heavy uranium, 238, had the ability to eat slow neutrons and digest them without much of an internal disturbance. It ate some of the slow neutrons coming in from the primary bombardment, and ate still more of the secondary neutrons which came out of the explosion of the 235 atoms, and which should have been available to maintain a chain reaction and produce explosions at a tremendously rapid rate. Atoms of the 235 isotope shattered with the greatest of ease, and each one of them started an atomic energy conflagration. But the atoms of the 238 isotope acted as fire extinguishers by consuming the neutrons that would have spread the fire. When the neutrons came out of the exploding 235 atoms, they were traveling at high velocity, some with energies of more than 300,000 electron volts. Even this amount of energy was not sufficient to smash the atoms of the 238 isotope, so it was immune to both fast and slow neutrons. These fire extinguisher properties of uranium-23 of May prove very valuable in the practical control of atomic energy processes. Nature seems to show great foresight in the manner in which she gives combinations of properties to matter so that man can use them efficiently for practical purposes. The slowing down of neutrons by water is a case in point. It is a most fortunate situation that the atomic energy release process using uranium-235 requires slow neutrons, and that the hydrogen atoms in water offer the best means for this slowing down process. Hydrogen atoms and neutrons have about the same mass. This makes it possible for the rapidly moving neutrons to transmit the greatest amount of their kinetic energy to the hydrogen atoms when they meet in collision. Even when a neutron has been slowed down to a velocity of 1/30th of a volt, about the speed of molecules of air at room temperature, it is still traveling at a relatively high speed, about twice as fast as a rifle bullet. When uranium-235 is used as an atomic energy source, the energy will be taken off in the form of heat. When an atom is smashed, its fragments fly apart at high velocity. They strike adjoining atoms and create disturbances in them which are transmitted to all other atoms in the mass, the resulting vibrations causing a rise in temperature. As the slow neutrons smash great numbers of atoms, the whole mass of the uranium-235 becomes incandescent. The water in contact with it, for the purpose of slowing down the neutrons, is converted into steam which can be drawn off and used to operate a steam turbine or other form of engine. The uranium performs the same service as the fire under the boilers in the ordinary powerhouse process, but the water serves in two capacities, one similar to that of water in the powerhouse boiler, and the other the most unusual function of making the fire burn, just as if in ordinary practice the coal were kept under water in order to make it burn. It is a most fortunate fact that the uranium-235 atom is shattered only by slow neutrons. If the process should continue at the rate at which it starts, the whole mass would be quickly transformed into energy in an amount too tremendous to utilize or control. In other words, an explosion would take place. But the master designer of the universe installed an automatic control process at this point. When the uranium becomes incandescent, the water in contact with it will be converted to white-hot steam. Water in this state will not slow down the neutrons. They will have the same temperature velocity as the steam and will be traveling too fast to act as efficient atom smashers. With no slow neutrons available to maintain the disintegration process, it will be suspended until the neutrons are cooled down sufficiently to come again in the atom smashing range, when the heating process will start again. This provides an automatic control that will make it possible to have the atomic energy processes operate continuously at some fixed temperature. This control process has an analogy in the governor on a steam engine. When the engine goes too fast, the governor cuts off the steam, and if it goes too slow, the governor opens up the steam valve, causing it to speed up, thus enabling the engine to operate at a constant speed. 4. Reference was made to the use of pure uranium-235 in the atomic energy process. It may be that this substance will never be used in its pure metallic state because of the probability that it would be entirely too active. It is more likely that uranium-235 will be alloyed with uranium-238, as it is probable that a mixture containing as little as 5% of the 235 isotope, or perhaps even 2%, may prove to be a very useful and easily controlled atomic energy fuel. A slab of the pure metallic uranium-235 would have fantastic properties in the presence of a neutron gas. It would look like nickel and would be very heavy, about 22 times as heavy as water. Its activities would belie its innocent appearance. If a person should bring his hands near this block of metal to grasp it, he would very quickly draw back, because the metal would become very hot, perhaps incandescent as he approached. The water in his body would act as a slowing down agent for the neutrons present, and the slowed neutrons would start the atomic disintegration process. If a slab of the metal were dropped into a tub of water, on the suspicion that it was a bomb, and this was the best way to keep it from exploding, the result would be surprising, for there would follow an explosion like a volcano letting go. The water would slow down the neutrons and the atoms would start to explode in a chain reaction, making the metal incandescent and changing the surrounding water to steam in an extremely small fraction of a second. It is obvious from the foregoing that if uranium-235 is ever isolated in massive metallic form, it is going to be highly desirable to keep it extremely dry and away from the neutron-water combination. It is probably necessary to have a mass of uranium-235 6 inches or more in diameter if the chain reaction is to be maintained in it. With smaller masses, it may be necessary to have a starting process in constant operation, because too large a percentage of the secondary neutrons may escape. There is every indication at the present time that it will be possible to control the atomic energy process so that power can be drawn off in such quantities as can be handled safely. But there is a possibility that if we use too pure a sample of uranium-235, the processes may take place at such a rapid rate that all the energy in a mass of the material may be given off in an instant before control processes can become operative. If this condition were brought about intentionally, we should then have not an atomic power source, but an atomic energy explosive. As an explosive uranium-235 exceeds present explosives in destructive power to the same extent that this atomic power source gives more energy than is obtained from the burning of coal, or about 5 million times as great, weight for weight. If we take into account only that small fraction of the mass of uranium-235 whose mass is transformed into energy, more than 3 million times as much energy is given out than comes from the burning of an equal mass of carbon and oxygen. Annihilation of 1 gram of matter, there are 453.6 grams in a pound, would release 62,500 billion foot-pounds of energy. This would be sufficient to raise the Empire State Building, weight 303,000 tons, 20 miles high. Or about a square mile of Midtown Manhattan could be raised several hundred feet high, with no provisions for cushioning the shock on the return trip. This amount of energy would be released from about 2 pounds of pure uranium-235, which rapidly exploded all of its atoms in a chain reaction. 5. Speculating on the possible application of a discovery is not an idle pastime. It is one means of evaluating the significance of the new development. It is the means of tentatively testing the ground that lies ahead on the course of progress. Courage, imagination, and a sound grounding in facts are prime requisites for useful endeavors in this field. It is unthinkable that we should fail to use constructively this new discovery of a way to release atomic energy. We should therefore thoroughly acquaint ourselves with its favorable and unfavorable aspects, and, if the former exceed the latter by a sufficiently wide margin, prepare to utilize it to the fullest extent, making full provisions for all the adjustments that will be required in our economic, social, and political structures, national and international. Our present civilization is dependent upon energy. The extent to which we use energy is one of the indices of the state of advancement of our civilization. We have been lax in the task of distributing justly the benefits accruing from the increased use of energy, and as a result, our economic structure is under a variety of stresses and strains. The greater the extent to which we use energy, the faster is the tempo of our civilization. This will undoubtedly be true of the era of atomic power which is now dawning. We should, therefore, make all necessary adjustments to put our economic structure on the soundest possible basis. Power, energy, enters into almost every activity of our lives. Our principal primary sources of power are coal, oil, and gas. If we state all of them in terms of coal, then each individual in the United States uses the equivalent of 7.2 tons of coal per year, or 36 tons for the average family of 5 persons. Translating this into terms of electrical energy, at the average powerhouse order of efficiency of 1.44 pounds of coal per kilowatt hour, each individual in the United States consumes, or has consumed on his behalf, 10,000 kilowatt hours per year, or 13,400 horsepower hours. This gives each individual 36.7 horsepower hours per day, or 1.5 horsepower hours working for him every hour of his life. Probably less than 20% is used directly in the home, and the remainder is used in operating trains, ships, airplanes, automobiles, farms, factories, and a variety of forms of services for his benefit. Our energy bill, in round numbers, is about $3 billion a year. The largest fraction of this becomes part of the cost of the goods we consume. If atomic power did nothing more than cut the cost of our energy bill in half, it would be a very valuable development. But this is only one of the minor blessings which it probably has in store for us. A relatively small quantity of uranium-235 installed in a heating plant in the home might supply enough energy to keep that house warm in winter and cool in summer as long as the house stands. A more probable development would be heating and air conditioning by electricity, bought at such a cheap rate that installation of a home power plant would be uneconomical. Our automobiles might have installed in them at the time they are built a fuel supply that would last as long as the car. One might be able to travel as many thousand miles as he wished without having to bother about fuel bills. Oil bills might become a minor item, very much smaller than at present, because the present gasoline engines would be replaced by quieter and more easily maintained steam engines with an extremely small oil consumption. Fuel costs for railroads, ships, and airplanes might be greatly reduced, thus reducing travel costs. Stratosphere travel might become common for airplanes, and we might make long journeys in much shorter time than is now possible. Railroads would probably stick to steam power, because, with the fuel and smoke nuisance eliminated, it should be cheaper and more convenient than electricity. Extensive sources of cheap heat might bring about great changes in our agricultural methods. In our homes, we could use a great many electrical labor-saving devices. It should be remembered, however, that only 10 to 20% of the present cost of electricity is due to fuel costs. The complete elimination of this item would reduce the cost of electricity in homes in New York City, for example, only from 5 cents to 4 cents per kilowatt hour. Power might become a negligible cost item in our manufacturing establishments. Larger and more efficient machines, and more of them, might be used. Goods might become cheaper, though it must be borne in mind that electrical power costs now comprise only a very small fraction of the cost of goods. Engineering projects on a gigantic scale might become possible. Central powerhouses should continue in operation. Many industries which do not now use electricity in certain operations because of the cost of the current should be enabled to do so. Among them would be the heavy chemical and iron and other smelting industries. 6. What are the economic effects likely to be? The first effect will be psychological. Many industries face a tremendously important cycle of change. Some will be established on a sounder foundation, and others will be eliminated. There are so many and such great blessings for everyone in the coming atomic power era that we should try to see that no one suffers unduly in the transition. If atomic power can be developed cheaply, the coal mining industry is going to suffer most. Should atomic energy come into general use, a necessary consequence would be that coal mining as an industry would cease. Coke production for byproducts in the steel industry would presumably continue, however, as a part of the chemical industry. The oil industry would be hit temporarily, but would thank its lucky stars that it has invested millions of dollars in scientific research. Oil as a fuel may pass out, but oil as a chemical raw material out of which an almost unbelievably vast array of materials can be made may be in greater demand than at present. Our home, furniture, clothes, and even some of our food may be pumped out of oil wells in the near future. The railroads may pass through a very trying period. Coal comprises 1/3 of their revenue freight. If atomic power comes into general use, this revenue will be lost. Railroads use about 80 million tons of coal a year, 1/5 of the total amount mined. Atomic power would largely eliminate this expenditure, but this saving would hardly be sufficient to make up for the loss in revenue. Extensive changes would have to be faced by the automobile industry. The motive power might be changed from internal combustion to steam, assuming, of course, that a satisfactory small-sized power plant could be designed. In this case, the most important change in design would be elimination of the fuel tank. The fuel supply for the life of the car would be built into it at the factory. The roadside gasoline and oil stations would go. The public utilities may have an intricate problem to solve. A new fuel that gives vastly more energy than coal, pound for pound, is bound to come laden with problems as well as opportunities. One of the interesting possibilities that is likely to come out of our studies of atomic physics is a new way of generating electricity without the use of rotating machinery. Under certain circumstances, neutrons, the most plentiful material in nature, emit negative electrons and are transformed into positively charged protons. This might become the basis of a new method of generating electricity in tremendous amounts, which would not require any apparatus for transforming heat into mechanical and mechanical into electrical energy. In other words, would eliminate boilers, engines, and dynamos. There is another phenomenon which possesses equally fascinating possibilities in this field. Radiation of certain energy values can, under the right conditions, be transformed into material particles, positive and negative electrons, which fly out of the point of transformation in opposite directions. An electric current is nothing but a cloud of negative electrons flowing through a wire, a dynamo merely moving the cloud. Any phenomenon which provides a supply of electrons or other electrified particles in sufficient amount has in it possibilities for becoming a means of generating electricity. We know of no way, at the present moment, of working out a practical method of making electricity under these plans. We can mark these down as unsolved, not insoluble problems. Other methods of releasing atomic energy are now in the womb of time. The process by which the sun and the stars generate enough energy to keep their giant masses in an incandescent state utilizes materials which are extremely plentiful on the Earth: carbon and hydrogen, the chief constituents of coal and water. The carbon digests successive hydrogen atoms until its normal atomic weight is increased from 12 to 15, the increase representing 3 hydrogen atoms. When the 4th hydrogen atom is added, which would change the original carbon atom plus the hydrogen atoms into an oxygen atom of atomic weight 16, the combination breaks up, yielding 2 particles. One of the particles is the original carbon atom, and the other is a helium atom. In the course of this process of building up a helium atom out of 4 hydrogen atoms, a large amount of energy was released. The 4 hydrogen atoms lost 2.5% of their total mass when they united to form the helium atom. This mass was transformed into energy. Such a transformation of 40 pounds of hydrogen atoms would result in the transformation of 1 pound of mass into energy, and this would produce the equivalent in energy of 11,700,000 kilowatt-hours of electricity. The carbon coal remains unchanged to repeat the process, and the supply of hydrogen in the ocean is practically inexhaustible. The period of gestation required for this discovery to be conquered on a terrestrial basis depends on the extent of the support given to our scientists. 7. It would be unfortunate if the impression were given that atomic energy is going to be made available to us merely by the waving of a magic wand, or the equivalent, in some minds, the undulating traverse of a fountain pen across a checkbook. There are many practical problems to be solved. In the first place, it should be understood that this first process, utilizing uranium-235, does not release the entire amount of energy represented by the full mass of the material, but only that portion of the total which is described as the binding energy of the nucleus, and which amounts to about 0.25% of the total mass. Even this, however, gives vastly more energy than the burning of coal of equal weight. The practical problem at the moment is the scarcity of uranium-235 and the difficulty of extracting it. Uranium-235 is obtained from the ores of ordinary uranium, which contains 0.75% of uranium-235. The principal source of uranium is pitchblende, a heavy rock that looks like tar, and which contains 65 to 92% of the metal as a black oxide. Nearly all of the mines from which this ore is obtained were located and developed shortly after the discovery of radium, which is also obtained from uranium. The largest pitchblende deposit is probably that in northwestern Canada, discovered a few years ago. There are 2 mines in Germany, one in the Belgian Congo, one in Australia, and one in Colorado, the latter having the uranium in a secondary form as carnotite. There is such a small market for uranium compounds at the present time that the prices are abnormally high. Granite rocks contain a small amount of uranium, and if the demand for the material is sufficiently great, many concentrations of the ore material will undoubtedly be found. Separation of uranium-235 from uranium-238 is difficult at the present time. It has about the same status now as did heavy water when Professor Harold C. Urey, Nobel Prize winner of Columbia University, discovered it a few years ago. It was then the rarest substance on Earth, but today it can be purchased in heavy concentrations and in large quantities from a number of commercial producers. The cost of separating uranium-235 from uranium-238 may prove to be an economic barrier to the use of this substance as a means of obtaining atomic power on a practical scale. The reward for bringing down the price, however, would be so great that we can reasonably assume that this will eventually be done. 8. There is another important phase of the matter which requires a great deal of attention, and that is the effect of neutrons on the human body. Neutrons, in some respects, act like X-rays. When a living organism is subjected to neutron bombardment for a long period of time, the particles appear to have a serious effect on the white blood cells, either stimulating the process in which the cells are destroyed or slowing down the process by which they are generated. Too great a destruction of these cells would lower the body's resistance to disease germs. Scientists who have been working constantly under the influence of neutron gas have thus far suffered no ill effects, but the periodic medical examinations occasionally show that they have a low white blood cell count, but still above the danger mark. There is another possibility, of a beneficial nature, in the effects of neutrons on the human body. Recent experiments indicate that they may offer a means for effectively treating cancer, at least superficial types, and other observations indicate that streams of neutrons may offer a more satisfactory means of reaching deep-seated tumors than a single beam of X-rays. The uranium-235 process produces a great supply of neutrons and will be of great use to scientists in producing artificial radioactive substances far more potent than can be produced in any other way. And these may also have important medical uses, as well as supply an important laboratory tool for effecting the now routine transmutations of the elements, thousands of times more powerful than the cyclotron. After due deliberation, in balancing the blessings, the possibilities, and probabilities against the handicaps and dangers, the net results appear to be an indication that the discovery of the uranium-235 process for the release of atomic energy promises the dawn of a new era for mankind.